Good morning or good afternoon, depending where you are in the world, and welcome to this presentation on the overground features of version 21, which was released right at the end of last year, 2023. My name is Philip Ike, I'm Marketing Director, and I'm assisted today in the technical sessions by Steve Rhodes, Technical Director, Andy Taylor, Support Engineer, and Julian Moses, our Training Manager. On your side, we have the mics off today for the GoToWebinar facility. We do, however, value your interaction during the session. In order to do that, you need to enter questions into the GoToWebinar panel. We will then answer those depending, either direct in the text chat. Some will be answered in a panel session, which we'll hold at the end, and some then will be answered after the event. So the format today is pretty simple. We're just about to get into the technical sessions. There are 4 of those. And then after that, we have the panel session for Q&A that will feature all 4 of us answering your questions live. And with that, well, let's get things started. So I'll hand over to Andy for the first session. Andy, over to you.
Thanks. The first new development I want to highlight in this webinar is the parasitic bar facility. This simplifies embedding reinforcement within a concrete model by allowing us to define the geometry of the concrete as an outline only and parasitically attach the reinforcement, defined as a bar element taking tensile or compressive loads. In this 3D volume model of a reinforced concrete pier and crosshead subjected to an impact load on the pier, I've created my concrete outline and meshed it already. Let's check our geometry using the new Dimensions facility. Under Attributes, Dimension Lines, you can choose what dimension you want. Let's get the global Z dimension, and let's put in an offset so that the dimension line isn't right against the model. Let's also choose to measure the global X dimension. We can then select lines that we want to assign these dimension lines to. And let's also do these ones for the X dimension. Alternatively, you can choose 2 points to assign a dimension to, and then the dimension line will be drawn from one point to the other. Let's turn those off now in order to clean up the display. We have our concrete geometry, so let's now add our geometry for our reinforcement. You can define the geometry directly within LUSAS, or you can import it from another file. We can import multiple different file types in LUSAS. I've created this reinforcement in a CAD package and transferred it via a DXF file. We now need to define our mesh for the reinforcement, which we use from Attributes, Mesh, Line, and use the new parasitic bar option. I'm going to make all of the volumes invisible in order to select just the reinforcement lines and assign that reinforcement mesh to them. The fact that LUSAS is now able to determine the mesh intersections while retaining the simple outline geometry means that should you wish to change the reinforcement in order to consider a different layout, it's incredibly simple as your concrete geometry remains unchanged. We then need to assign our dimensions. I'm going to start off by assigning a 12mm bar to all of those lines, and then I'm going to select just the lines at the top of the crosshead in order to overwrite that with a 20mm definition. We also need to assign a material property, so I'm going to assign nonlinear steel to the reinforcement. Let's talk a little bit further about the materials. For the concrete material, I'm using a nonlinear cracking and crushing material proprietary to LUSAS. In this material, we can define the limiting tensile stress beyond which cracking will occur, as well as the compressive strength beyond which crushing will occur. For the steel material, we're using a von Mises yield criterion beyond which increasing deformation can occur without an increase in stress. These nonlinear materials allow us to model the behaviour of reinforced concrete, where localised cracking can lead to tensile load being taken by the reinforcement, which if loaded enough, will yield. Let's switch to model results. I could have solved the model I had open, but there are a large number of mesh intersections between the concrete elements and the many reinforcing bars, so the meshing would take between 2 and 5 minutes, and then solving for results would take the same amount of time again, with a relatively large number of elements in a non-linear analysis. If we look at the results for the pier impact, let's look at the Layers tab. What we're looking at are contours of stress on the bar and values of cracking and crushing within the solids. If we zoom in at the impact location, we can see the crack planes shown in these black squares at the point of impact. And towards the bottom of the pier, we can see cracking in the concrete and higher stress in the reinforcing bars there, as the reinforcing steel is taking a tensile load where the concrete is cracked. Rotating it round to the other side, if there's any concrete crushing, we would see black stars here, but there's no concrete crushing occurring, which is good. You'd rather see steel yielding before concrete crushes. This demonstration has been with a 3D model, but the same principles apply within a 2D model too. Advanced concrete analysis with embedded reinforcement, simplified in LUSAS version 21. It's now over to Steve, who will tell you about the FCM wizard.
Thanks, Andy. So yes, the free cantilever method, or FCM wizard, which you'll find in the bridge menu here, is a new facility to speed you through the creation of a stage construction model for a balanced cantilever bridge. And on this first page, you can see that my model was set up with SI units, but of course you can use other units as you wish. And I'm going to start with the example bridge for speed, which already has some sections up here created. And in each drop list, you can select from those that are already defined or choose new, which will launch the usual dialog, giving you access to the section libraries and calculators. And similarly, the material drop lists here offer any existing concrete creep and shrinkage materials, or you can use the new option. In the loading section, crucially, we can include the weight of the wet concrete. That's sort of in situ terminology. If we were using precast segments, then equally that could represent a segment being lifted into position. Over on the right, let's just modify the example to make this a curved bridge with a reasonable plan radius. And let's add a pier, which of course means adding a span as well. We can also indicate here that the piers are not all the same. That might be because they're at different heights, or in this case, because they are built sequentially rather than simultaneously. Let's put a 3-month delay for each pier. We click next and have to give the necessary dimensions for the blocks in the taper zone, the construction period and the concrete age at the end of the stage, because of course precast concrete would be older than the time taken to complete the stage, whereas in situ would be younger. Similarly for the pier height, actually 6 meters seems a bit short, so I'll make that a bit bigger. Block 0 sits atop the pier legs, and again dimensions and times or ages are needed. And finally there's a key joint which connects the internal spans. The example had 2 piers, so using this button at the top of the tab I can copy the input from the first pier to the other tabs. Of course they may be different, but often very similar. Over on the right, the fully staged parts at each abutment require a few sort of similar inputs. At any point we can save our progress, because obviously a large complex structure might take a bit of time to input. When we click next, we move on to the tendon input pages, and in the cantilevering sections, if I scroll through some of the construction stages and zoom in a bit, typically we have tendons in the top slab, type 1, and those in the webs, type 2. There are lots already filled in for us in this example. I'll just delete them now, and we can enter a couple just to see how it works. The delete button here would usually delete just that row, but I'm deleting them all. So I click the plus button to add a tendon, and if I don't know what those input dimensions are, I click help, scroll down, and I can see that the X dimensions are the length of the tendon from the center line of the pier, and the H dimensions are measured down from the deck top surface. Now if I enter 1.5, 6.5 as my length, and 0.15 and 0.5 as my heights, and radius of 3, you can see that the tendon appears and the stage is automatically entered as 4, because that is the stage when the block where the anchorages fall is installed. If I just scroll back, I can give a lateral offset of 4 and tick the symmetric box. Now I have 2 tendons for the price of 1. If I use the copy button, I get another row, and if I make x2 12.5 say, and an offset of 3, then we can see that the anchorage falls another block or 2 along, and so that tendon will be installed in stage 6. Of course, I also need to specify the tendon properties, and you can probably find the code of practice that interests you in this list. And of course, don't forget to enter the tendon area and check the other parameters on the right here. And the tendon force is conveniently entered as a factor of the ultimate tensile strength. So you can see it need not take all that long to enter the 20 or 30 tendons needed. And I can copy my tendons from pier 1 to the other piers as I did for the pier data. Similarly, if I click next, we can add the continuity tendons and the tendons for those end sections. The final stage of the wizard allows us to preview all of the details of the stages before we click finish. And the wizard will create a model that's ready to solve. It will have all the sections, materials, supports, loads, stages, tendons with losses, and so on that we specified. And here it is. We can just step through the load cases clicking the plus button, and there, pier 1 doesn't seem to have too many tendons, but pier 2 a bit more sensible. I can just jump across to a model now which was created more reasonably than that one, has more tendons, and which has already run through Solver. So we can see the moments and stresses here in stage 17. That maximum moment 343 is just to the left of the pier. If we zoom way out, we never lose that number. And then we can step through the stages again, or we could use the animation wizard on the tools menu. But anyway, you'll see that the deformed shape is actually going upwards, because of course the pre-stress opposes gravity and has to keep everything in compression. But whichever way that should rightly go, we can select the points in the deck and run the bridge construction table. Lots of options here, but the default for a camber table with a target of a flat deck in the final stage gives us the target location for each segment when it's placed, and at each stage, as it might go up and down a little, so that we can meet that flat target. We can check that against construction on site. Now, before I hand back to Andy to talk about vehicle load optimization, maybe I can just take a moment to add the sky and the ground. I find the tile size around 300 meters works, and position, that's 26 meters down. It's the height of the piers plus the thickness of the deck. And to make this look a little better, we can change the lines to be coloured grey rather than magenta. Now it looks better, but to me it looks a bit dull. So I find the new illumination options, just adding the shadow and increasing the lumens to about 300 for this model, it can give us a quite nice looking plot. So you can see the new functions in version 21 there, from the FCM wizard through to the diagram labels and the new graphics options. And with that, it's back to you, Andy.
Thanks. In this demonstration, I'm going to talk about our latest additions to aid grillage analysis, and then take a look at VLO envelope runs, a significantly improved facility for vehicle loading optimization. This is a grillage model built in dimensions of feet and inches using the grillage wizard. Under Attributes, Geometric, Bridge Deck Grillage, we've now added multicellular decks and shear key deck options. We now offer section calculators for all bridge deck types, covered in Hambly's Bridge Deck Behaviour, one of the leading references on grillage analysis. This particular bridge is a multicellular deck. If we open up the cross-section definition, we can see here the inputs that we've put in for the longitudinal cross-section calculation and the type of cross-section it creates. And for transverse, we can see the dimensions we've put in for that. Let's now carry out a vehicle load optimization using the new method. Under Attributes, Influence, as well as the previous methods or pre-existing methods, we also now have the Envelope option. You choose the effects you want to optimize for, and whether or not you want to include coexistent effects. I'm going to assign the influence to my entire model, everything that has mesh. You'll notice the first improvement, that this new influence type can be assigned directly to geometry features, such as lines, surfaces and volumes, rather than just to the mesh. This means that any change to the mesh in your model will not invalidate your VLO results. I'm then going to select my curb lines and go to Bridge Vehicle Load Optimization using the new VLO Envelope Run option. I'm going to run this for United States AASHTO Code of Practice, and I'm going to run it for Strength 1 only. You'll notice that many of the options under Solution Process have disappeared. This is because they're no longer needed, as the VLO envelope behaves like other results load sets. And when we choose our influences, you'll see there are fewer options here as well. This is because VLO envelopes automatically do both positive and negative effects, and for design codes like AASHTO, which have different loading patterns of piers, LUSAS will now automatically determine which locations these apply to. We define our carriageways as in the previous version, and then we would click OK in order to calculate the vehicle loading. But for the purposes of this demonstration, I'm going to switch to a model which already has the results solved. VLO envelopes are a significant speed and efficiency improvement over the older VLO options. Rather than creating load cases for each individual effect at each selected node, requiring the model to be solved for these load cases, VLO envelopes are able to get the results directly from VLO. This new method requires far fewer calculations to be carried out, which creates much less data. It also makes it practical to run VLO for the whole structure, rather than requiring engineering judgment to select a few critical nodes. For this particular model, it takes about 5 to 10 minutes to solve, and we find this is about 6 times faster than the previous method. So in this model, we can see we have our VLO envelope in the tree view, and just like any other envelope, it's got a maximum and a minimum. Let's set it active for the maximum and optimize for MY. And we can see here straight away the results for the optimized maximum bending moment anywhere on the structure. You'll notice another version 21 improvement here, where the values for different nodes are overlapping. Some are faded out to make others easier to read. Obviously the values with the largest magnitude get priority, but as we zoom in, the values get further apart on the screen, allowing more and more to be displayed. Obviously, our maximum bending moment is going to be over the pier. If we want to know what loading causes this load case, we can select the node at the pier, and then select an adjacent element, and right-click to visualize loading at the node. LUSAS will then show what loading was used in order to calculate the effect at this node. And what we can see, it's not very clear, the purple lines showing the uniformly distributed load and the red arrows showing the vehicle loading, but we've got in each lane a truck either side of the pier, and if we expand we can see it is the dual truck. So 90% dual truck and a 90% design lane, which is the AASHTO loading for moments over the piers. So as I said beforehand, the VLO envelope has automatically determined that this is a pier location, and therefore it should be using this effect. This load case is only temporary. If we wanted to save it, we could right click and copy, but otherwise when we turn off to visualize loading at the node, that load case will be deleted. As the VLO envelope is like any other sort of envelope in LUSAS, we can directly put it into a combination. So let's create a combination with 1.25 factor for the dead load, 1.5 for our surfacing, and we can leave the live load at a factor of 1, and it's already been factored by the vehicle load optimization. VLO envelope runs in LUSAS version 21, a significantly improved facility for vehicle loading optimization. I'll now pass over to Julian for the final demonstration.
Thanks. Now I'm going to use this trussed footbridge to look at two of the new facilities in version 21. Now the first one is a projected wind load. So loading, distributed load, and it's this projected wind load that I'm going to work with. Now I'm going to project my load in the Y direction. So this is transverse to my structure. And I'm going to use a load intensity of 1 kilonewton per meter squared. I'm working in newtons, so 1000 newtons. Now when we project this, it will work out the surface area of each of the members based on their size and calculate the correct loading to be assigned to each member. So I'm just going to call this wind load, and I'm going to assign it to one of the trusses. Now I've already got a group in my model, so I'm going to go to the groups and I'm going to select those members, and you can see I've got this truss here, and I'm going to assign my wind loading to those members. Now I've signed this into the linear static analysis into a load case called wind loading. Now once I've done that, I can rotate the model around and look at the loading, and you can see it's being applied to those members. And once I've checked that it's been applied, I can solve the model and look at the results. Now I've actually got two analyses in this model, but more about that later. But here you can see the lateral wind loading is causing a lateral deflection. Now in this model, I use the wind load with a constant pressure. But if I go to my attribute again, I could actually add a variation to my pressure, and that variation would allow me to vary the load intensity or the pressure with height, so I can have a lower pressure at ground level and a higher pressure higher up the structure. And that's useful if you're looking at, say, a mast or radio tower. So that's wind loading in version 21. Now, as I said, I've got two analyses in this model. Now, if I look at the results of this, these are a natural frequency analysis. Now, the mode that I'm looking at here is lateral at 1.6 Hertz, and this is a vertical mode at 3.05 Hertz. Now, this is important because we're going to try and excite this using the new Pedestrian dynamic analysis wizard. Now, to do that, basically, I'm going to close my results down, and I'm going to create a path across my structure. So I'm going to create a line that's slightly longer than the bridge in each direction. So minus 17, 0 and 17, 0. Now I've put this line down the middle of the structure. Now there's no real guidance given to where this should be, but you could perhaps try a couple of locations across your structure. Now with this line selected, I'm going to go to the bridge menu, and I'm going to use the new Pedestrian moving load analysis to set up a dynamic analysis. Now, first thing I need to do is define the pedestrian definition. So I'm going to go new, and you can choose one of the design codes we have, or you can use a general dynamic behavior. So if your situation isn't covered by design code, I'm going to use the Euro code here, and I'm going to look at a group of people jogging across my structure. I'm going to have the bridge class as C, so that's urban environments. And this is the frequency that I showed you earlier. So I'm going to type in this as 3.05. The reduction factor that I'm going to use, I'm just going to use the default here of 0.8. Now, as well as the vertical components, I can also add additional components in the lateral or longitudinal direction. Now, in this case, I'm going to add some lateral vibration as well, and I'm going to use the default value of 12.5%. So as well as vertical vibration, I'm going to have a lateral vibration. Okay, so I'm going to call this a pedestrian definition, and okay. And now I'm ready to assign this definition to my model. Now I've already got a search area on the bridge, and this is the bottom members, and I've called that deck. And I'm going to assign the load to a reference path, and I'm going to send it in the forward direction, doesn't really matter. And I'm going to use a time step of half the default value. So rather than 0.01, I'm going to use 0.005. Now, this is going to create 2,266 load cases. Now, that's going to take a few minutes to produce and run. So rather than waste time here, I've got one already that I've created, which I've just switched to. And this has the results loaded so I can look at them straight away. Okay, so the first thing I'm going to do is look at a graph of the loading definitions. So here you can see I've got a graph of my vertical excitation and my lateral excitation. So you can check what's being applied to your model. I'm going to close those down. So the next thing I'm going to do is a graph of acceleration. Now, it's this acceleration that you'll use to look at the comfort criteria on your structure. Now, I've picked this node at quarter span, and I'm going to do graph wizard and a time history graph. Now, in the X direction, I want a named component for the pedestrian dynamic analysis, and that named component is going to be response time. Now, in the Y direction, I'm going to look at nodal, and I'm going to look at the vertical acceleration. And that's the node that I selected. So there's my graph properties. Now, the only thing I've done is switch off the show symbols option here. So if I hit finish, my graph of response time versus acceleration will appear. I'm just going to edit the graph slightly to pick a thicker curve. Just stands out clearer. So this is my graph of acceleration versus response time. And it's this peak value here I would check against the design code criteria to see whether the bridge passes or fails the design code checks. Okay, so that's some of the new facilities in version 21. I'm now going to hand back to the presenter.
Right, thank you for that, Julian. So that takes us to the end then of the technical session. So I'd just like to summarise some of what we've seen obviously today. So we began with the modelling of rebar, that's shown by Andy. We moved on then to the FCM wizard, the cantilever method wizard, shown by Steve. Then to load optimization, the whole structure load optimization, and finishing there with Julian doing the pedestrian dynamics. Now during this time, we've been taking questions, and we're going to go through some of those now and give you some answers, I hope. So if I can ask the other panelists to set their mics active, then we'll come in here and answer some questions.
Okay. Do you want me to take a question, Phil?
Yeah, Andy. Yeah, if you wanna start with.
Okay. So I can actually there's a few similar questions here about license requirements. So for the various facilities that we've shown in this webinar, a couple of people asking what license requirements are for those. So let's cover those. So if I talk about the demos I did, so for the embedded reinforcement, in order to do that meshing, you can use any license at all. So in order to do the meshing of the line within a volume or within a surface, any license at all can do that. But the particular demonstration I did, which used non-linear cracking and crushing concrete material and a non-linear yielding steel material, you will obviously need a non-linear license. In terms of the vehicle load optimization, the VLO envelope, that comes with any normal VLO license. So if you have VLO, you will have the VLO envelope option. Julian, do you want to talk about your one?
Yeah, the pedestrian moving load analysis has just been added into the bridge menu. So you don't need a license to access that. But obviously it is doing a time history analysis. So you will need the dynamics option within LUSAS to do the full analysis, but you don't need a separate license just to get hold of the wizard. And I think the final one is Steve's.
Yeah, likewise, really. For the FCM wizard, you can run that from any, I guess, bridge license, and that you're running the wizard, so you can enter all your data, and that's obviously a substantial kind of little job if you're designing one of those bridges. But you won't be able to build a full kind of nonlinear and transient, i.e., a creep analysis model, without owning the nonlinear and transient license. So, I mean, you could have someone working on that wizard and then passing it over to a colleague who has the nonlinear license, if that makes sense.
Yeah, absolutely. Andy, just another thought on the rebar is for curing of concrete, because what you've shown there is the cracking due to mechanical input, if you like. But if you're looking at the and transient situation of curing, then that's something you could also do with that capability.
Yes. So if you want to do a heat of hydration analysis, looking at a large concrete pour, looking at the thermal effects during the curing process and whether cracking occurs and whether you've got enough reinforcement in there, then yeah, the embedded rebar parasitic bar facility, very useful for that, but you will need a heat of hydration license in order to do that sort of analysis.
Okay, great. All right. Any other questions we want to answer here? We've had a few left, I think, on this particular session than we have the previous couple of days.
Yeah, I'll take one on, again, on the embedded reinforcement. The question is, why would I use this facility with the embedding the reinforcement rather than just doing a simple beam analysis for my concrete reinforced concrete structure? And the answer is, if you can use a reinforced concrete frame with beam elements for your type of analysis you want, absolutely go ahead and do that. And we have a reinforced concrete frame designer for beam models, and also reinforced concrete slab and wall designer for shell element models. And if you can use those, then you absolutely should. This particular facility that I was showing is more for where you've got more complicated situations where you can't use that sort of simple analysis. So maybe a concrete hinge, as shown in that 2D image at the end of my demonstration. That 2D hinge the concrete hinge you can't really cover with basic code capacities. So doing the finite element analysis using the embedded reinforcement is the way to go.
I suppose the other thing, Andy, is things like deep sections where it just doesn't really correspond very well to a beam analogy for doing a frame.
Yeah, so when your beam analogy falls down when you're looking into deep sections, then again, yeah, that facility is very useful.
Okay. We are going to keep
one on wind loading.
Sorry, Julie.
Yeah, there's one that's coming for the wind loading. When I showed the wind loading, that's obviously calculating the pressure based on the surface area of the members that are being hit by the wind load. So if you've got a bigger member, you'll get a bigger amount of pressure. Now, I didn't show it, but you can obviously visualize the values. Now, you can do that through the print result wizard, or you can switch the values later on. So you can actually view the actual loading effects on the model, so you can check whether it is actually doing what you think it's been doing in there. So it's not just the blue arrows, you can see the actual pressures on the individual members.
Thank you. We just had a couple of queries that have come in right now, if the panel want to look at those. One on the DLO and one on impact.
Okay, so sorry,
go on, Andy. Okay.
Steve, go.
Okay, yeah, I'm interrupting on your VLO facility there, aren't I, Andy? The question has two parts. The first part, in a sense, is really can you use what you showed, Andy, on a grillage model, but not on a 3D model? And that's not the case. You can use what Andy showed on grillage models, 3D models, any type of model. Basically, it works for. The other part of the question is, when do we anticipate including the centrifugal forces, which are included in AASHTO in the VLO? And that I have to answer because I've been looking at it recently. Yeah, the development is actually complete. So it will be in the next version of LUSAS, and we hope to put a dot release out during the year before we come round to the sort of annual end of year version. I guess we've had version 22 this year. So hopefully it'll come to you pretty soon.
Okay, and the other question I was going to answer was the peer impact analysis. Was that a static or dynamic load? So that was just a static analysis I was carrying out. LUSAS can also do dynamic analyses as well. You will need a dynamic license in order to do that. But yeah, we can do dynamic analyses as well. Just that in terms of getting a simple model to show in this relatively short demonstration for the webinar, I stuck with only doing static loads for this demonstration.
Yeah, so
I mean,
if you, yeah.
I was just going to add, I think it's worth saying that we do have clients who use LUSAS for blast analysis and that sort of thing. So they are actively using that kind of concrete damage model together with other non-linear materials and so forth with that kind of dynamic loading. Yeah, what you did was very reasonable. I think most bridge engineers would recognize a kind of pseudo-static equivalent to an impact load.
Yeah, the other thing I was going to add as an obvious damage and potential application of dynamics would be seismicity and then the damage on a structure from an earthquake. And similarly, obviously, you could calculate the cracking during the seismic event using our transient facility to do that. All right, I think we are pretty much. Shall we? Let's move on. As I say, we can. There are some sort of smaller questions, if you like, which we'll come back to separately. So I think beyond that, let's start to wrap up. So obviously, the session that we've shown you today is the overgrounds, part of our series. And for those of you that have been paying attention to our marketing, we split version 21 up into 3 different areas. So overground has been this week. We're also going to do an underground series of webinars. And I think actually next, Julian, if you want to talk about this a little, we've got some connected webinars upcoming as well.
Yeah, we'll probably be doing a connected webinar in February, and that's probably going to be looking at Rhino and Grasshopper, but we'll bring in some of the other components. We'll probably talk about the Rivet application as well. So that's likely to happen in February.
Good. Okay, great. All right. Well, look, I think that pretty much concludes the event for today. So thanks everyone for watching wherever you are in the world. You know, this is sort of intended to be centered on the US. It's sort of relatively comfortable for the North American time zones, but wherever you are in the world, thanks for being involved in this. And if the other panelists want to just join me in saying their goodbyes.
Thanks for your time, guys.
Yep, thanks.
Yeah, thanks for listening, everyone. Any further questions, do type them in. I will try and answer them. Otherwise, thanks and goodbye.
Yeah, goodbye indeed, and see you at the next event. Thank you.